Okay, all right. Hello again, everyone. In the second part of the talk, I'll be presenting Blend. Blend is published in Nucleic Acid Research Genomics and Bioinformatics journal. So you can reach the paper and the source code using these QR codes. I'll give an executive summary quickly. So finding exact matching seeds, exact matching subsequences between sequences introduce limitations in further improving the performance and accuracy of genome analysis. So our goal is to enable finding the fuzzy seed matches or approximate seed matches, as well as the exact matching seeds accurately and efficiently. So Blend provides effective mechanisms for converting seeds into a set of items to use with hashing technique known as SimHash technique. And Blend uses the SimHash technique to enable generating the same hash value for highly similar seeds to find fuzzy seed matches with a direct lookup of hash values. Blend provides significant speedups up to 40x and lower memory footprint up to 7x compared to Minimap2, especially when using hi-fi reads, highly accurate reads. It also improves the accuracy of important genomic applications such as de novo assembly and structural variant problem. So let me quickly give you a brief background again on genome analysis, but I won't spend too much time on it. So high throughput sequencing machines extract smaller fragments of original DNA sequence that we know as reads. And the challenge is to perform genome analysis from these small random pieces so that we can extract again some information from them. And to do so, we commonly use these reads to identify genomic sequence similarities in two ways. First, we can map these reads to previously constructed representative sequence of a species called the reference genome. Mapping reads to a reference genome helps us identify the potential mapping locations of reads in the genome, as well as identifying the exact differences and similarities between the read and the reference genome. The second option is to overlap reads to each other. So overlapping reads identifies the matching regions between reads, which then can be used to construct de novo assemblies from these overlaps. But these similarities must be identified efficiently and accurately to facilitate a practical genome analysis. So, for example, mapping reads to a reference genome usually requires expensive computation on a large number of reads and a potentially very large source space. So, for example, a human reference genome contains more than 3 billion characters. And indexing the sequences enables practical search over a large number of database of sequences. And hash tables are usually commonly used data structures for indexing. So this index can contain some subsequences that we call k-mers extracted from the reference genome and the list of locations of these k-mers in the reference genome. Identifying the sequence similarities using hash tables involves several heuristics. For example, the seeding step quickly finds matching k-mers between a read and the reference genome, which determines the regions in the reference genome potentially similar to the read. So the chaining or seed filtering techniques enable further reducing search space from all seed matches to fewer regions by pruning the regions that are unlikely to be similar to each other. So for the remaining regions, computationally costly sequence alignment is commonly used to identify the exact differences and similarities between a read and the reference genome. So let's look more into identifying seed matches using hash tables between a pair of sequences. Here, the first and second sequence can be regions from a reference genome and the read, respectively. So there are several sketching techniques that extract some subsequences from these two sequences so that we can find seed matches between sequences. So we will call these selected sequences seeds. So to efficiently identify seed matches, so these seeds are hashed using some low collision hash function and stored in a hash table. And to find matching regions between these two sequence pairs, we also find the seeds from the second sequence, hash them, and query the hash table using these hash values. So this method can quickly tell us if there is a seed match or not with a single lookup of hash values. So then let's go over some seed matching techniques, or the seeding techniques that we have to identify these subsequences that we extract. So I'll go over 3 of them quickly. So there are some techniques that can sample the overlapping k-mers, for example, minimizers. And the goal is to essentially reduce the storage space requirements when matching the seeds. So here we have some overlapping k-mers in a window of k-mers. And what we do is that we hash all of these k-mers, but pick only the minimum one. So the idea, again, by picking only the minimum one, we're going to be reducing the storage requirements significantly without hopefully reducing the accuracy too much, let's say. And here the window length plays a crucial role in determining the accuracy of this mechanism, also the performance. Also, there are some seeding techniques that can allow us to tolerate some mismatches at certain positions when matching these subsequences to each other. For example, there are seeding techniques called space seeds, and this is how they work. So given these subsequences, we apply some patterns on them, meaning we essentially insert some don't care characters at certain positions. And so we then, like, by inserting these don't care positions, we call these sequences that we generate space seeds. But the idea is that instead of hashing these sequences, we hash space seeds, meaning we can identify some matches, seed matches, because their hash values would match, although the matching seeds, or the original version of these matching seeds, would include some mismatches between them. And we can tolerate these mismatches by including some don't care characters in the space seeds. So here the choice of pattern is critical for the effectiveness of the space seeds. Furthermore, we can also allow some insertions and deletions when matching the sequences to each other. For example, we can use a seeding technique called link k-mers or stopmers. And the idea here is that instead of matching these sequences to each other directly, what we can do is that we can select some of these k-mers within these sequences. For example, we can use minimizers to identify these k-mers, and then we can link these selected k-mers to construct a new sequence. So we call these sequences that we generate stopmers. And rather than matching these sequences, we try to match them by generating their hash values. So the idea is that the stopmers can match, although the original version of their sequences may be including some insertions and deletions between them. So by matching these stopmers, we actually tolerate these insertions and deletions. So, but here the idea is that in all of these seed matching techniques, the seeds are essentially hashed so that we can find seed matches with a direct lookup of these corresponding hash values. So in this case, for example, we have space seeds, and then here we hash them and then generate their hash values and then use hash tables to find the hash matches. And to do so, usually low collision hash functions are used. So this means that the seeds must exactly match to generate the same hash value. Meaning, for example, here, if you want to generate the same hash value for a particular space seed, then the space seeds should be exactly matching. So the advantage of this mechanism is, of course, that these similar seeds are unlikely to match. But then the limitation is that the highly similar seeds, meaning fuzzy seeds, are also unlikely to match. So I'll try to convince you regarding the challenges of exact matching seed techniques. So exact matching seed techniques introduce fundamental limitations when adjusting the many seeding parameters. For example, the k-mer size. For example, should the k-mer be long or short? Or, for example, in the case of minimizers, should the window length, for example, be long or short? Again. And all of these choices essentially determine the content of the hash table, which then has a substantial provides a substantial trade-off between performance, memory, and the accuracy of genome analysis, because we determine all these parameters by assuming that the seeds must exactly match. So then what will be the opportunities of fuzzy matches of seeds? So a mechanism for finding fuzzy seed matches or finding approximate seed matches can enable assigning the same hash value to highly similar seeds. So these seeds may not be exactly matching, but they can still be highly similar to each other. And a fuzzy seed matching technique would then ideally be generating the same hash value for these highly similar seeds so that we can match them efficiently. But still, we would want to generate different hash values for dissimilar seeds. And it should still provide high performance. For example, no distance calculation or similarity calculation should be performed to identify these fuzzy seed matches. And it also should be space efficient. For example, we don't really want to do or use multiple hash functions for a single sketch, meaning we don't really want to increase the content that we're storing in the hash tables. So finding fuzzy seed matches can enable finding useful and novel seed matches that cannot be identified when finding only exact matching seeds. So it also enables us to rethink the seeding parameters to achieve the better trade-off between performance, memory, and accuracy. So with that, I'll go over our goal and the key ideas in Blend. So our goal is to enable finding fuzzy matches of seeds, as well as exact matching seeds, with a single lookup of hash values of these seeds. So to this end, we propose Blend. Blend uses a hashing mechanism known as SimHash that can generate the same hash value for similar sets. Blend provides the mechanisms for accurately and efficiently converting the seed sequences into set of items so that we can use these set of items with the SimHash technique. So I'll briefly show how SimHash works to generate the same hash value for a similar set of items. So this is an example input that a SimHash can take as a set of items. Here, the entire sentence is the set, and the items of this set are the words in the sentence. So SimHash can generate a single hash value for the entire set using the hash values of items. The hash values can be generated using a low collision hash function. So here we show the hash values in their binary form. Then to generate a single hash value for the entire set, SimHash calculates the net difference of ones and zeros at every bit position. And stores these difference results in a counter vector. Here we have the net difference results for each position. The leftmost, for example, the leftmost value shows the difference results of the most significant bit. Zero shows here there are equal number of ones and zeros. The rightmost is for the least significant bit. Positive values show that there are more ones than zeros at a particular position. And here the negative values show there are more zeros than ones. Then the result of this majority voting can be translated into hash value again, where each bit position is set to 1 if the corresponding position in the vector is greater than 0, meaning there are more ones than zeros at the particular position, at the particular bit position in the entire set. So by simply looking at each position in this binary, we can directly tell the majority voting result of each bit position. So one important property of SimHash is when there are two highly similar sets, where only a few items differs from this set, it can still generate the same hash value because the majority voting result is likely to stay the same for two similar sets, although the results in the counter vector may change. So let's go over this using an example. Here we generate a word. This means that we again change the hash value in the corresponding set again, and the net difference result in the counter vector also changes. However, the majority result of ones and zero bits are still the same at every position, so we can generate the same hash value for highly similar sets. So now the challenge is to use this nice property effectively and accurately by converting the seeds into a set of items. So to achieve this, we use blend with the SimHash technique. So our goal in this blend is to efficiently find fuzzy seed matches with a single lookup. And the input to a blend is a fixed length subsequence, for example, a seed sequence. And blend efficiently and accurately converts the seed that it takes as an input into its set of items using two conversion mechanisms that we provide and that we call blend I and blend S. And using these set items, we can now use SimHash technique to generate a hash value of the set, which is essentially the hash value for the seed. Then we can efficiently identify fuzzy seed matches by matching the SimHash values using a hash table. So let me quickly go over how the blend I works, one of the sequence to set conversion techniques. So the input to blend I, the goal in the blend I is to convert the seed sequence into set of items so that we can use these set of items with the SimHash technique. And the input is, again, a fixed length subsequence. Here is a seed sequence. And what we do is that we extract all overlapping k-mers from the seed that we call neighbors. And then using any hash function, for example, low collision hash function, we generate the hash values of these neighbors. Then essentially, these hash values represent the set items for the entire set, which we're going to use it with the SimHash technique. So this is also how blend S works. I'm not going to explain it in detail, but essentially, rather than extracting all overlapping k-mers from a seed, we only extract linked k-mers in the sequence if we're using a linked k-mer strategy, for example. And then similarly, we extract the hash values of these linked k-mers, and then we use these hash values as the set items. So now that we identify the set items using either blend I or blend S, we can use these items with the SimHash technique. So the goal is to generate the SimHash value of a seed using its set of items generated from blend I or blend S. So what we do is that we encode these hash values using vectors of zeros and ones. Here we have, for example, -1 for 0 bits and +1 for 1 bits, because essentially the negative values are going to represent the majority of 0 bits at a particular position, and the positive resulting majority voting is going to be representing the majority voting result for 1 bit, let's say. So essentially, by using these encoded vectors, we perform a bitwise summation to generate the counter vector. And using this counter vector, we perform decoding to generate the hash value for a particular set of items, which is essentially the hash value for a seed. So meaning we can now use this hash value using the hash table to identify fuzzy seed matches. So we envision that the blend can actually be integrated with any seeding technique, but in our work, we integrate blend with two seeding techniques, which are the minimizers and the stoppers. So to integrate the blend technique with minimizers, we use the blend I mechanism. Here, these are the k-mers, overlapping k-mers in a certain window, and then we generate the hash values of these k-mers using blend I, and then we pick only the minimum hash value from these, and then use them with the hash table by picking only minimum one similar to a minimizer. Again, in stopmer seeds, once we identify the stopmer seeds, we can use them with the blend test technique to generate the hash values of these stopmer seeds so that we can identify the fuzzy seed matches. Although these stopmer seeds may not be exactly matching, we will still be generating the same hash value if they are highly similar to each other using the SimHash mechanism, essentially. So I'll show our results quickly. So we integrated blend into Minimap 2 to perform end-to-end mapping. In our evaluation, we use real and simulated data sets from PacBio. So these are both HiFi, highly accurate, and CLR data sets, erroneous data sets. Also reads from ONT, Oxford Nanopore Technologies, and also Illumina reads. We use genomes, human genomes, CHM13 and HGO2, fruit fly, yeast, and E. coli genomes in our evaluation. So we have two use cases. The first use case is read overlapping, or all versus all overlapping. Also, what we do is that we evaluate the accuracy, completeness, and the contiguity of de novo assemblies generated from these overlaps using Blend and other tools. And in our second use case, we perform read mapping to a reference genome, and we calculate the mapping accuracy from simulated reads. We also perform structural variant calling and then calculate its accuracy. So before showing these results, I want to quickly show the empirical analysis that we do on fuzzy seed matching. So here, this figure shows several configurations for Blend and the Minimap2. And what we do here is that we identify non-identical minimizers with the same hash value, meaning we identify the collisions. And we show the ratio of these collisions and also the edit distance between each pair of minimizers with a colliding hash value. So our goal in this blend is to increase the collision rate for highly similar seeds while keeping the same collision rate for dissimilar seeds. So here, this bar, the green bars show the collision rates for Minimap2. And what we see here is that we have a nice Gaussian distribution over here. There is a high collision rate for slightly dissimilar seeds using Minimap2. And Minimap2 is using essentially a low collision hash function. And these are the results for Blend. And what we observe is that the Blend increases the collision rate for highly similar seeds, meaning we increase the collision rate, selectively increasing the collision rate for the highly similar seeds, which, for example, here have an edit distance of 2, while keeping the collision rate similar to Minimap2 for dissimilar seeds. So then let me go over the performance and the memory results that we evaluate in read overlapping. So here this figure shows the CPU time in the y-axis in the top figure, and also the peak memory usage in the bottom figure. And we have the results for different data sets as shown here. And we compare Blend with Minimap2 and MHAP, two popular state-of-the-art tools for read overlapping. So although in general, we provide better results, I'm going to be mainly focusing on the HiFi results. For HiFi, Blend provides an average speed up of 40x compared to Minimap2. It also reduces the memory footprint by 7.2x. So we can achieve these improvements because we can improve critical parameters without hurting the accuracy, as we can find fuzzy seed matches that the other tools cannot find. For example, we can increase the window length up to 200 and seed length up to 21 MERS. So we also show the read overlapping accuracy results when we generate the assembly. Here, like we have different data sets focusing on, again, the HiFi data sets. And these are different metrics showing the accuracy for the accuracy and the completeness, regarding the accuracy and completeness of the genomes. In general, what we observe is that Blend provides more accurate and complete assemblies compared to Minimap2 and MHAP again. And it also provides better contiguity in most cases. So we can achieve this because fuzzy seed matches can lead to finding novel and useful overlaps that the exact seed matching techniques cannot find. So this is the read mapping performance and memory results. These figures are similar to the read overlapping performance and memory results. And we compare Blend to many read mapping tools. And in general, what we observe is that Blend provides an average speed up of 1.7x compared to Minimap2, and it provides also similar peak memory usage. So we don't have like as accurate, as good results as we have in the read overlapping, because what we find is that the computational cost of sequence alignment slightly hinders the benefits of fuzzy seed matching. So lastly, I'm going to be showing the accuracy results that we generate using structural variant calling. So what we do is that we identify the structural variants using the read mappings from each tool. So we use Sniffle's tool to call the structural variants from HGO to long read mappings. And then we use TrueVary tool to compare the resulting structural variants with the benchmarking structural variant set, which is the ground truth set as released by the Genome Analysis consortium. So this table shows these accuracy results. Here we show true positive, false positive, false negative precision and recall, and also F1 scores for each tool. And what we identify is that, especially when focusing on the F1 score, which is a general representation or general look for both precision and recall results, Blend provides the best overall accuracy in downstream analysis, again, thanks to finding these unique fuzzy seed matches. So then I'll quickly conclude. Again, finding exact matching seeds introduces its own limitations in further improving the performance and accuracy of genome analysis. And our goal is to find fuzzy seed matches as well as the exact matching seeds accurately and efficiently. To this end, Blend provides the effective mechanisms for converting the seeds into set of items so that we can use this set of items with the SimHash technique. So SimHash technique can generate us the same hash value if the set of items are similar to each other. Blend provides significant speedups up to 40x and lower memory footprint up to 7x compared to Minmap2 using hi-fi reads. And it also improves the accuracy of important genome applications such as de novo assembly and structural variant code. So this is the QR code to access the paper, which is published in the Nucleic Acid Research, Genomics and Bioinformatics. And this is again the QR code to our source code. With that, I'll conclude the Blend talk, and I can take questions.
Any questions?
Thanks for a really nice talk. My question is, have you tried evaluating the benefits of using Blend with more noisy reads? Like you evaluated on hi-fi, I think, right? Which have like 1% error rate. Mm-hmm. Have you tried on higher error rates?
Yes. So let me see if I have it in my background. So these are the data sets that we used. And among the data sets, we have slightly erroneous reads, which is coming from ONT reads. And also we have reads from PacBio CLR data sets. So these are slightly erroneous than the hi-fi reads. And although I guess I showed these results in my previous slide, let me again quickly go back to it. So these are the results for the erroneous part, so the noisy reads. And again, by looking at these results, what we again in general see is that Blend still provides a better accuracy and usually reduced memory footprint, but the speedups and the memory footprint reduction is not as good as that we see in the hi-fi reads. And this is essentially because those reads are erroneous, noisy, and this means that we cannot really adjust these critical parameters as much without losing from accuracy. So the parameters that we use these data sets, that we use for these data sets are a bit more conservative, let's say. That's why we're not providing as impressive results for these particular data sets.
Thanks.
Okay, thank you again, Can. And